Hello, my name's Roger Watson and welcome to this session on common statistical tests. If you turn to a typical statistical textbook and try to find what sort of test you should use easily, you're normally faced with an algorithm like this, which is often presented inside the front and back covers. These look a little bit daunting and complicated for a start. They're all variations on the same theme. However, they aren't that complicated to use. What they're trying to lead you towards is deciding whether you're using a single sample and you're describing it, or two sample or three samples or more, and then what kind of data you're using, parametric or non-parametric. Now, I'm just going to say at the beginning of this session, and I'll explain why, we're only going to look at parametric tests in this particular session, and these are by far the most commonly used. I'll explain why we're going to do that in a few slides. So, despite the fact that we're going to look mainly at parametric tests in this session, it's still worth considering what kind of data you have. It's always a good first step. So variables can be either scale or categorical. Scale data can be continuous, the kind of measurements we use every day, weight, height, time, and so forth, and these can actually take any value at all, including decimal places and fractions, or they can be discrete, for example, number of children. Categorical data can be ordinal, in other words, it can be ordered in some way, for example, on a Likert scale from strongly agree to strongly disagree, or it can be nominal, which doesn't provide any meaningful order, things like ethnicity, gender, hair color, where you live, or whatever. So different kinds of tests, strictly speaking, need to be applied to these different kinds of data. And that's because these different data give you very different kinds of estimates of central tendency and spread. Scale data, if it's normally distributed, you can use the mean and the standard deviation to describe the data. If the data are skewed, then you should use a median and an interquartile range, and the same applies to ordinal data. Nominal data, you can only use the mode, you can only count the number of categories there, and there's no measure of spread associated with it. So we're going to be looking at normally distributed data using parametric tests. We're also going to look at one exception using nominal or categorical data. So the kind of statistical tests that you use depend on what kind of dependent variables you have. The dependent variables are the ones that change or vary as a result of your research conditions. We'll look at dependent and independent variables later in the session. If the dependent variables are scale variables and they're normally distributed, you can use parametric tests, the kind of tests we're going to look at today. If they're skewed or ordinal, strictly speaking, you should use non-parametric tests. And if they're nominal data, there really is only one choice, and that's the chi-square test, which we will cover later on. Now I'm going to say something which is heretical to most statisticians, I'm sure, but the textbook by Bryman and Kramer on using SPSS for quantitative data makes a bold statement that if your numbers are large enough, there essentially shouldn't be any difference between using parametric and non-parametric tests. And I have actually demonstrated this myself with a large data set where I ran both parametric and non-parametric tests and got absolutely no difference. We sometimes, however, don't have the luxury of large data sets, and if you do have a small data set, and if you are in any doubt, then you should probably use the non-parametric equivalents of the parametric tests. We're not going to cover them here, and probably you should be asking yourself the question, especially these days, if your numbers are very small, then why are you using statistical tests in the first place? So I'm going to make the assumption here that you've got a large data set that's normally distributed and that we can use parametric tests for it, except for the example of nominal data that I'm going to cover later in the session. Just for completeness, we'll look at a couple of tests of normality, just if you want to check if your data are normally distributed. One way is quite simply on SPSS to plot a histogram of your data. That's quite easy under the graph functions, or you can do it under the descriptives. You can also run the QQ plot, which plots your observed value against an expected normal value for the data, and the straighter that line, the more parametric your data are. However, I'm just showing that for completeness, so we're not actually going to be concerned with that here. We're going to make the assumption, as I've said a couple of times, that the data are normally distributed, or that they're a large data set if they're not necessarily normally distributed, and that we can apply parametric tests. So basically, which test should I use? Well, common single comparison tests include the independent t-test, the one-way ANOVA, the paired t-test, and the repeated measures ANOVA, which we're going to look at in this session. By single comparison, I just mean comparing one thing with another. We'll also look at a couple of tests of association. One is Pearson's correlation coefficient, that's a parametric test, and we're going to look at the chi-square test, which is for nominal data. And if you've got several independent variables, we will have a quick look at the ANCOVA test, the analysis of covariance test. Those are all the tests that we're going to look at in this session. How I'm going to do this is to preface each test with an example to show you what you might be using the test for. So first of all, we're going to look in example one at, is there a difference between one group and another? For example, is there a difference between males and females, or is there a difference between nurses and patients on the score on a questionnaire? Now in this case, the dependent variable, the one that you're interested in, is the score on the questionnaire, and the independent variable, the one that you can't have any influence over, is either gender in the first example or professional group in the second example. The appropriate test to use in this case is the independent t-test. The dependent variable, the score on the questionnaire, is continuous, and the independent variable is binary, in other words, grouped. So the t-test is used to compare the means of the two independent groups, and the independent groups means that different people are in each group. To interpret a t-test, if the p-value is less than 0.05, there's a significant difference between the means of the two groups. And you should report the means of the two groups, or the mean difference. There's no reason why you can't report both, and the confidence interval of that difference, which you can obtain from the SPSS output, and this describes the difference. In SPSS, you enter analyze, into compare means, then independent samples, t-test, and after that you follow the instructions for entering the data. Example 2 looks at, is there a difference between one time and another? For example, is there a difference in a test score before and after a teaching session, or is there a difference in a diagnostic score after treatment? Here the dependent variable is the score on the test or the diagnostic questionnaire, and the independent variable is described as a level, in other words, the time before or after, or treatment or not before and after treatment. And in this case, we use another kind of t-test. It's a paired t-test. The dependent variable is continuous. It may well be interval, but we can treat it as continuous, and the independent variable is time point 1 or 2, or the condition, treated or not treated. A paired sample t-test can only be used when the data are paired or matched. Either they are before or after measurements of the same variable, or the t-test can be used to compare how a group of subjects perform under two different test conditions. The test assesses whether the mean of the paired differences is 0. And the interpretation is if the p-value is less than 0.05, there's a statistically significant difference between the two time points or the experiments, and report the mean difference. In SPSS, you go into Analyze, Compare Means, Paired Samples t-test, and follow the instructions for entering the data there. Example 3 is there a difference between two or more groups? Again, it's on the score on a questionnaire. For example, is there a difference between children, adolescents and adults, or is there a difference between doctors, nurses and patients? Now, you may think that what you need to do here is to do different t-tests, for example, doctors versus nurses, doctors versus patients, and nurses versus patients. However, that isn't the way to do it. What you need to do is test them all together and then test to see where the differences lie. In this case, the dependent variable is the score on the questionnaire and the independent variable is the age group or the professional group. The test of choice here is the one-way ANOVA. ANOVA stands for analysis of variance. In fact, that's the basis of all these statistical tests, all the parametric tests at any rate. Dependent variable here, as we already know, is continuous, the score on the questionnaire, and the independent variable is categorical, and there have to be at least 3 categories. So to use the test, it's used to detect the difference in the means of 3 or more independent groups. It can be thought of as an extension of a t-test for 3 or more independent groups. Strictly speaking, the t-test is a special case of the ANOVA, but never mind. ANOVA uses the ratio of the between-group variance to the within-group variance to decide whether there are statistically significant differences between the groups or not. And the interpretation, ANOVA tests, here we've got H0, in other words, the null hypothesis that all group means are equal, and it uses an F test as opposed to a t-test. The p-value concludes whether or not there is at least one pairwise difference. In other words, at least one pair is significantly different. And if the p-value is less than 0.05, we reject the null hypothesis. In other words, we accept there is a significant difference between at least one pair of means. Post hoc tests are used to test where the pairwise differences are, and then you report the significant pairwise differences and the mean values. There are a range of post hoc tests or post hoc adjustments, Tukey, Sheff and Bonferroni. In my experience, Bonferroni is the easiest one to use, or the most common one to use and the most common one to understand. What these tests do is to reduce the p-value at which you accept a significance between the groups, and it adjusts according to the number of groups. The Bonferroni is the simplest one to understand because it simply divides the p-value of 0.05 by 3. So in fact, the significance level you're looking for when you've got 3 groups is not 0.05, but 0.017. That aside, in SPSS you go into Analyze and then into the general linear model. For the ANOVA you choose univariate, or you can compare means and you can use ANOVA. There's 2 different ways to do it. You can go into Analyze, Compare Means and use ANOVA, or you can go in this way. So there are different versions of the ANOVA. They're slightly different, but for all intents and purposes they will give you the same outcome. Example 4 is the difference in a score on a questionnaire at 2 or more times under 2 or more conditions. For example, is there a difference in a diagnostic score at time 1, time 2 and time 3? Or is there a difference in a diagnostic score under treatment 1, treatment 2 and treatment 3? Here the dependent variable is the diagnostic score and the independent variable is the time or treatments, and these are considered, as we've already seen, as levels. The test of choice here is the repeated measures ANOVA. The dependent variable is continuous, as we know, and the independent variable is categorical with levels as with what's called the within subject factor. That helps you to know where to enter those data when you come to using SPSS. In this case, the within subject factor number would be 3 because there are 3 different levels. So the use of the test, it tests the equality of means in 3 or more groups. All sample member characteristics must be measured under multiple conditions. In other words, the dependent variable is repeated. This is the equivalent of a one-way ANOVA, but for repeated samples, and is an extension of the paired samples t-test. Again, strictly speaking, the paired samples t-test is a special case of the repeated measures ANOVA, but that aside. It's used to analyse changes in mean scores over 3 or more time points or differences in mean scores under 3 or more conditions, as we've already said. And the interpretation is if the main ANOVA is significant, there's a difference between at least 2 time points, and the Bonferroni post-hoc tests will conclude where those differences are. Report the significant post-hoc results and the means at each time point. And of course the post-hoc adjustments can be made, and the most common one here is definitely the Bonferroni test. So to find the repeated measures ANOVA, you go into SPSS, Analyze, General Linear Model, and then Repeated Measures. Now example 5 is there a relationship between one variable and another? For example, is level of pain related to analgesia, in other words to the amount of analgesia, and is depression related to quality of life, if you measure them both on some sort of measures for depression and quality of life respectively. Now, the dependent and independent variable is not always easy to identify or even necessarily sensible to identify here, because we're looking at correlation, and correlation does not mean causation. However, in the first example, the dependent variable would clearly be pain, and the independent variable, the one that you're varying, is the analgesia, and it's the pain that you're interested in. However, in example 2, depression and quality of life, trying to ascertain which is dependent and independent is quite difficult. So really, you've got to be clear when you're using correlation, which is what we're looking at here. You're looking at a relationship and not necessarily at causation. And this is what a correlation looks like. Here's the pain versus the level of drugs or analgesia. This is just for interest, a negative correlation because it goes from top right to bottom left. But a correlation looks to see if the various relationships between one particular level of pain and one particular level of drugs, as plotted here over a range, is statistically related or not. Is it just random, or is there a line? And the correlation method fits a line of best fit to this, and that's what's analysed, and it's the difference of these dots from that line that's analysed to give you the actual correlation. So the appropriate test is Pearson's correlation coefficient. This is a parametric test. The dependent variable is continuous and the independent variable is continuous. In other words, both variables are continuous. And Pearson's correlation coefficient is the most common measure of correlation. It measures either rho or R, rho for population correlation and R for a sample correlation. More often than not, of course, you're dealing with a sample and dealing with R. In SPSS, you go into Analyze, Correlate, and then bivariate correlation and enter the data there. So correlation is used to measure the strength of association between two variables and ranges between -1, a perfect negative correlation, to 1, a perfect positive correlation. We're just going to look at the positive correlation, which in fact ranges from 0 to 1. And in this case, the interpretation, there are different versions of this, I have to say, but interpretation here, there's 0 to 0.3 is weak correlation, 0.3 to 0.5 is moderate, 0.5 to 0.9 is strong, and above that is very strong. We don't usually concern ourselves too much with the probability from correlation tests, because you will observe using these tests that nearly always the probability is less than 0.05. and in fact the correlation is related to the sample size. So you can get very small correlations which are really meaningless, and they can be highly statistically significant. So in this test we don't normally pay too much attention to the statistical significance, although you would report it. Example 6 is being in one group or not related to being in another group or not. For example, is being in an inoculation group or not related to being in an infected group or not? The dependent variable here is the infected group, being in that or not, and the independent variable is the inoculation group or not. Again, however, we are looking at relationship in this example. We're not necessarily always able to discern the direction of causation. Here we can represent this in a contingency table. This is a 2x2 contingency table, and you can see that there are two groups on the left, inoculated or not inoculated, and two groups along the top, infected or not infected. This is from an actual study done many years ago. These are real data. You can see quite clearly, just looking at that, you probably don't need statistics to tell you that being inoculated clearly reduces the number of people who are infected. Now, the appropriate test to test this is the chi-square test. Chi-square test is a non-parametric test, but it's the only test you have for testing these kinds of associations. And both the dependent and the independent variables in this case are categorical. In other words, they fall under the nominal type of data. So you use this test to test if the null hypothesis that there is no relationship or association between the two variables is true. The chi-square test compares expected frequencies, assuming it's true, with observed frequencies from the study, and when obtaining a significant chi-square result, you calculate the percentages in a table to summarize where the differences between the groups are. So having a test and simply finding out that it's significant is not enough. You do need to represent the data properly to show where the differences lie. That isn't always as easy as you may think. Also worth pointing out here that chi-square can be used for more than 2x2 tables. It can be used for any size of table. However, there are disadvantages. In very large tables, say 10 by 10 tables, you're likely to get lots of cells within the table which have nothing in them or very small values, and that affects your test. So the interpretation is if p is less than 0.05, there is a significant relationship between the two variables. For 2x2 tables, you need to use a particular correction called the Yates correction. This is automatically applied by SPSS. And in SPSS, you go into Analyze, Descriptive, Crosstabs, and then Statistics. That's how you find the chi-square test. You use chi-square test to test the relationship in the crosstab, which is a contingency table. There is another chi-square test in SPSS, which comes under the another category, but that's a slightly different use of chi-square. If you want to test a contingency table, this is how you must do it. And some people get confused about that and use the wrong test. And finally, example 7. Now, example 7 is something that I don't want to go into in too much detail. I just want to introduce you to it. It's the analysis of covariance test. And the example is there a difference between one group and another? Is it dependent on a confounding variable? For example, is there a difference between males and females if the females are significantly older than the males? So let's just imagine you've done a test, an experiment, or a survey. You've gathered data from men and women, and then you've looked at the demographics and you've noticed that the mean age of the women is older than the men, and you've tested that using a t-test, found it to be statistically significant. But nevertheless, there is a difference between males and females when you test them in the raw, as it were, when you test one group against the other. However, you may be asking yourself, well, maybe it's because they're older that the females have this difference. You can't really tell. So the appropriate test is the analysis of covariance. The dependent variable here, of course, is the score on the questionnaire. The independent variable is gender, and the confounder or the covariate is age. As I've already said, the appropriate test here is the analysis of covariance, known as ANCOVA. The dependent variable, the score on the questionnaire, is continuous. The independent variable, which is your gender, is categorical, and the covariate is continuous. Here you need to go into SPSS, Analyze, General Linear Model and Univariate, and follow the instructions there and add the covarying variable during the analysis. And this should tell you whether or not the effect of the age or the age difference is having an effect on the outcome between the men and the women. If it is, then your result will no longer be significant. If the result is significant in the presence of that variable, of the covariate, then your difference between the male group and the female group is real. So finally, looking back at this diagram that we looked at the beginning, it may begin to make a little bit more sense to you now. Not all of the tests that I've mentioned are on here, and in fact you can find better examples of this, which will include the chi-square test and so forth. This one also gives you, as you'll see, in grey, the non-parametric equivalents if you do want to use them. However, don't worry too much about this particular diagram. It's just an example of the kind of diagram that you will find in statistical textbooks. Some are more complete than others. So hopefully that's given you some idea of where you might use various statistical tests based on the examples that I've given. Thank you very much for listening. That's my email. If you have any questions or comments, you can check my background and publications on ORCID if you want to. You can follow me on Twitter, or you can contact me via WeChat. Once again, thank you very much for listening.